Okay, let us start the second part of our session. So to introduce Professor Alberto Saldaña, we have Professor Luz de Teresa to introduce him. Thank you, Lucero.
Okay, so it's a pleasure to introduce Alberto Saldaña. As I was telling before, it's one of our young researcher, but he's not so young. So he finished his PhD 10 years ago in the University of Frankfurt under the advisor of Tobias Webb. And he did after some he had other postdoctoral positions in the Brussels and Lisboa, and also in the technological of Karlsruhe. I don't know how to pronounce it. Okay. So he's now at my institute in Mexico. So he's at the Institute of Mathematics at UNAM, and he's going to talk about some recent results on weakly coupled elliptic systems. So thank you, Alberto.
Thank you for the very nice introduction. I am very happy and very honored to be part of this seminar. Yes, just looking at the list of all the speakers that have been here, I really feel honored to be part now of this seminar. So thank you very much for the introduction. So I'm going to talk about some recent results that I have obtained with my collaborators. The group of researchers that have been involved in the results that I'm going to talk about today are Monica Klapp, who's also in our institute in UNAM. There is also Professor Andrzej Szulkin from the University of Stockholm, Professor Jorge Paya from the Universidad Austral de Chile, and we have two postdoctoral researchers in our group also, Victor Hernandez Santamaria and Felipe Angeles. So together we have been exploring different aspects of weakly coupled elliptic systems. So the general formula for this kind of systems is the following. We have diffusion term in terms of the Laplacian, then maybe some potential multiplying a zero order term, and on the right hand side we have some nonlinear couplings. We can have L equations. Here L belongs to the natural number, can be one or more, and omega is a domain, an open connected set in Rn. Now, different results from what I'm going to talk about have different assumptions on the potential and on P, but basically these are the generic assumptions. P is either critical or subcritical. So whenever P equals 2 star over 2, we say that this is the critical case. 2 star is the critical sub exponent. So it's infinity if I'm in dimension 1 and 2. And it's this 2n over n minus 2 if we are exactly in dimension 3 or higher. About the coefficients, which we call the coupling coefficients, well, whenever ij is different from j, we will ask them to be negative. So we are in the competitive case. And beta ii is always positive. Okay, and the potential usually is going to be uniformly bounded. Sometimes you're going to take it identically 0, sometimes identically 1, and sometimes really in this generality of being uniformly bounded or with some integrability. Some noise. Thank you. So to fix ideas, let me show you two examples of this kind of systems. If I have two components, and let's say that I ask them non-negative so that I can get rid of these absolute values, then, for example, I can take p equal to 2 in dimensions 1, 2, and 3, and I get this very famous system called the cubic system, and it's very famous and very well studied because it has some relevance in applications in physics, in Bose-Einstein condensates and in Kerr-like photorefractive media. But we can also consider different powers p. For example, I can take p equal to 3/2 if my dimension is 1 to 6. And now I perhaps lose the physical motivation, But nevertheless, these systems have a very interesting mathematical structure, and studying them and developing methods to understand the set of solutions is a very important and interesting and fun topic to study. So if I take this power p equal to 3/2, I want to emphasize that since I have here my p minus 2, I will get a square root on the coupling term. So this is now a sublinear power, and it's going to cause several problems later on. So sublinear powers are related to several pathologies in terms of some qualitative behaviors. And then I always have this superlinear term helping somehow. Okay. By the way, let me emphasize that my p is always in this range, possibly critical. So whenever my n goes to infinity, so the larger the dimension I get, this one it's closer to 1. So I always need to be having a smaller p in large dimensions in order to have this subcritical notion. Okay, so a very good thing about these systems is that they have a variational structure. So I can find solutions by finding critical points of an associated energy functional. The energy functional looks like this: gradient term, L2 term, and coupling term. Okay. The other interesting thing about these systems is that since they are competitive, they exhibit segregation. And we can see this idea already from the energy functional. So because my beta is negative and I have this kind of term in my energy functional, this whole term is non-negative. So solutions which typically will like to have least energy or low energy will prefer to have almost no interaction. They would prefer to have separated supports as possible, whenever possible. So let me use some numerical approximations to illustrate this segregation phenomenon. Now I'm going to use not really the nonlinear system that I have told you. Let me use a Lotka-Volterra system, an evolution system, just to illustrate what this segregation means and how can we picture them in our heads. So this is a reaction diffusion problem, and we have here a logistic nonlinearity together with a coupling term, which now is really just lambda times uv. This is a competitive Lotka-Volterra system, and I'm using this because this is more tractable from the numerical point of view. So you start with some initial conditions, you let the evolution go, and you see that whenever you put some reasonable initial condition, they segregate quickly. It's very, so in this case, I am using this lambda large, which is like 10, and we see that quickly they segregate. This, when we have 2 species, now with 3 species, they also want to live in their own space. It's too hard for them to be fighting all the time, so they prefer to just have their own part of the domain and be happy with it. If we have 4 conditions, then we still see this segregation. This is the initial condition that I put into the numerical simulation, and this is the evolution that I get. Of course, my initial condition was a little bit cooked up. So it is a stochastic, a little bit, there is some stochasticity there, but I made sure that the initial condition gave all the species the same fighting chance. So we are not starting, and the red one is not starting with more elements than the green one. They are all more or less equally at the beginning. They have equal movement, equal birth rate, and equal fighting chances. So under these conditions, there is not a possibility that one dominates the other. They segregate. And if we look at this picture here at the end of the evolution, so to speak, we see some very interesting stuff. So now the ball is divided into 4 sets, and they are more or less the same set, right? If I take this one, I can get the other one by just rotating it, and I'm not getting different geometries here. Also, the solutions have the same property. If I get, let's say, the orange one and I rotate it, I get the red one, and if I rotate it, I get the green one. These kind of arrangements, we're going to call them the pinwheel solutions, and this is going to be a pinwheel partition of my domain. Now, several questions appear, like when I can find a pinwheel solution, and if this is splitting my domain in some optimal way, so this is optimizing something, what is this something? How can I explain if this is an optimal partition, what is being optimized? Okay, so these are some questions that we're going to answer or try to answer in this talk. So let me start. Okay, so competitive systems. Now we can ask several questions in this setting. We can ask when least energy solutions exist, when we have multiplicity of, let's say, positive solutions, when we have non-existence, perhaps under some domains, under some circumstances, there will be no solution at all. What about the qualitative properties of the solutions? If I have decay or if it satisfies some unique continuation, when they do, when they don't. Also the limiting profiles. So this beta, here there is a beta, is the competition parameter. So if I have like super large competition, then my profiles will really, really segregate, and the limiting profiles, we would expect them to have disjoint supports. And now the support of each of the components maybe gives rise to this optimal partition that we were talking about in the previous slide. So let's study as far as we can this type of objects and also these pinwheel solutions, these pinwheel partitions. Let me start with these pinwheel concepts, pinwheel solutions and partitions. Can we find them? And we will be starting already with a hard problem, a critical problem. So no potential, and my P is really 2 star over 2. So I will have here 2 star and 2 star over 2 in the coupling terms. And the question is, can I have, and we are in Rn, so we will be looking at solutions, pinwheel solutions in Rn. And let's see if whenever I let my competing coefficient go to infinity, I obtain a pinwheel partition. So do these solutions exist for this problem? Well, the thing about the critical exponent is that these problems have a lack of compactness. The lack of compactness comes from invariance under dilations. This means that if I have any function u in my space, let's say d1, and I make this dilation, then this is a transformation that cannot be seen with the norms in my space and with the norms in my energy functional, because the gradient norm remains invariant under these dilations, and the L2 star norm is also invariant under these dilations. So I can start with this blue function, and then I dilate it, and then I get, let's say for epsilon 0.01, I get the orange one. And then if I go a little bit smaller, I am still concentrating. So my solutions in the critical world are allowed to vanish by concentrating in one point. And we need to avoid this if we want to find a solution. So these critical problems, because of these pathologies, also have several non-existence results. For example, this critical problem in omega doesn't have any solution if my domain omega is star-shaped. Let me put here also Dirichlet boundary conditions. So there is no solutions of this problem in this kind of domains. Okay, this already is telling me that maybe these shapes are not the right ones, because all these shapes are star-shaped, right? This is like a cone, and cones are star-shaped. So if I want to find pinwheel solutions, I will have to use a different type of symmetry. It's just not so simple as just rotating them. Okay, so in collaboration with Jorge Falla and Monica Clark, we found an example of some symmetries that allows us to have pinwheel solutions and a pinwheel partition. And let me explain you what is this symmetric setting. Okay, we have it for dimensions n larger or equal 4, but let me focus on the case n equal 4 just to fix ideas. O4 is the group of linear isometries in R4, reflections, rotations. And let me consider the group G of elements of O4 such that I rotate an angle of theta, the first 2 components, and then I rotate in the opposite direction the last 2 components at the same time. Okay, so this is this is how the elements of my group G look like. And R is just a rotation. I can represent them by a rotation matrix, for example. We say that U is G invariant if whenever I apply my symmetries, they don't change. So for example, this would be an example of a function that is G invariant whenever it only depends on the norm of x1, x2, and the norm of x3, x4. Oops. Then necessarily they're going to be G invariant. All right, now what about the pinwheel structure? If it's not just a rotation, how can I go from one component to the other by a linear isometry? Well, we found this strange symmetry that actually works. So now we consider L functions, and we say that they have a pinwheel structure if I can get one component from the other by using this M transformation. And the M transformation looks like this. I will be rotating the first and the third component, and then I rotate on the opposite direction the second and the fourth component. Okay, it's a little bit counterintuitive why something like this would work, but when you do the computations, you see that this is a structure that is compatible with the G invariance, and that will actually give me a good Sobolev space with symmetries where I can do variational methods. So the result, together with Monica Clapp and Jorge Falla from last year, says the following. If you are in dimension 4 or larger and you're considering a critical competitive system, then this will have a non-trivial least energy pinwheel solution. So a function that is G invariant, and you can always get the next component from the previous one by this linear isometry G. All right, so basically the Sobolev space that we use is this one. We are using vector functions. Each component is G invariant, and you can always get one from the other by applying this linear isometry. Now, what about the optimal partitions? Let us start by defining what is an optimal pinwheel partition. So we say that a domain is G invariant if the orbit, whenever I apply my symmetry group, remains in my domain. Then a set of L domains is going to be an optimal pinwheel partition if the following 4 conditions hold. The first one is that each element in this arrangement of L sets, each element is non-empty. They are all disjoint. Whenever I is different from J, they cover my whole space, and each omega I is open. Then the second condition that I'm going to ask is that in each of these domains, omega I can solve the critical problem for just one equation. So in particular, these are not star-shaped. They cannot be star-shaped. Okay, so P2 tells me that I can solve the critical problem in omega I, and I can find G invariant solutions. Then my third property is that I can get the next omega, the omega I plus 1 from omega I, by just applying my transformation M. So omega 2 is obtained from the previous one by just applying M. And the same with all of the other domains. So it's like the rotation that we saw in the numerical approximation a while ago, but now we're using this M transformation, which is a little bit less intuitive. And then what is this thing that is being optimized? Well, in this setting, perhaps it's a little bit an indirect cost function, but it helps us characterize what's being optimized. So what is being optimized is the energy of the solutions in omega I. So I find my solution and I can compute its energy, for example, with the L2 norm of its gradient. And if whenever I add all these energies, then I search for a minimizer. So what are the domains that really minimize the energy of the corresponding solutions in each of these subdomains? If I find one, then I have found an optimal pinwheel partition made out of these patches of domains. So the strategy now is to take the competition parameter, let it go to -infinity, and then we show that a least energy solution of my critical competitive system will have a limiting profile. The limiting profile is going to be continuous and non-trivial. They will have always disjoint supports. If I restrict the limiting profile to its support, then I get a least energy solution of the critical problem under the condition that they are G invariant. These supports are an optimal L pinwheel partition. And there is a bonus. If I have only two limiting profiles, so I'm just considering two species, if I get one and I subtract the next limiting profile, I get a sign-changing solution of the critical problem in Rn. So how to understand this? It's very simple. So let's say that we had already some segregated, okay, so we are in Rn, so let's say that this was going to infinity. And what this last point is telling me is that I can just swap the sign of this last component, and the thing that I get is a solution of my problem in Rn. Okay, we can only do this whenever we have two equations. We don't know if in general this can be done. Perhaps yes, perhaps we cannot. This is an open problem, but at least for two we could. Okay, we have done this for a critical problem in Rn, but we can also do this, let's say, on the sphere. Now we would have a competitive system on the sphere with the Laplace-Beltrami operator. We can put also some symmetries on the sphere, let the competition parameter go to -infinity, and obtain an optimal partition. In this case, it's not a pinwheel partition, but it's some partition. And we have done this in collaboration with Andrzej Sulkin and Monica Klapp in 2023. So this is just like a quick mention of this result. We didn't invent the method. There are several other papers working with different types of competitive systems that take the competition parameter going to infinity and then study the properties of the limiting profiles, their regularity, their shapes, whether they've been optimized. And this is just a short list of this type of results. They are considering different operators, different manifolds, different symmetries. These here are also for systems that are not necessarily variational. So there is a huge literature with this kind of tools and with this kind of methods. All right, let us go to another question. How many positive solutions are there for this kind of competitive systems? Now, let me go to the subcritical world and let me add a potential identically 1. If I am looking at this system, how many positive, in a ball, now let me restrict this problem to a ball. How many positive solutions can I find for this problem? And I am also going to add here an epsilon square parameter. These kind of systems are sometimes called singularly perturbed. And the thing is that when the epsilon is very small, I am reducing the diffusion. So this helps these components to concentrate also on points. Now they concentrate not because some dilation invariance, but they are concentrating because of this epsilon factor in the diffusion. Okay, the question is, for this new problem, how many positive solutions does this system have? Well, let us start with just one component, one equation. If I look at this problem in a ball with Dirichlet boundary conditions, then it's a well-known result that there is only one positive solution. This was a result that can be obtained as a consequence of the work by Kwong, Lee, Ni, Nussbaum, Strickland, and Sang. So if my problem is subcritical, there will be only one unique positive solution of this setting, and it doesn't matter what epsilon is. Epsilon can be large or small or whatever. Then I can always find one unique positive solution. What happens if I now have two equations? A system with two equations. Then there is a result by Wang and Liu and Wu from 2013 saying that there will be two positive solutions at least. One, which is going to be the least energy solution, which looks like this. It concentrates two different components, concentrate in two different points. The points of concentration optimize the distance between them and the distance to the boundary. Because my boundary is toxic, my boundary is always Dirichlet, no? So they don't want to be close to each other, but they also don't want to be close to the boundary. This is a solution that is expected to appear, the least energy one. What is surprising is that there is another one. There is another one which will have two other concentration points. And it's not completely clear how to characterize these 2 points. We just know that they exist and that there is this other positive solution for this problem. Okay, so now what we answered together with Monica Clapp and Jay Suki is, if you have now L equations, what do you have? Well, you have L positive solutions. The more equations that you have, the more configuration of concentration points you can find. Only for epsilon small. Now, this is an important hypothesis. We need epsilon small in order to use this concentration phenomenon in these type of equations. But for this epsilon small enough, you can always find at least L positive solutions. The proof is done by exploiting the variational setting, some Lusternik-Schneiderman theory, configuration spaces, and barycenter maps in order to find some bounds on the category of some Nehari manifold. Okay, so this is what we found about multiplicity of positive solutions. What about unique continuation? Now let's go to study a little bit more the qualitative behavior of the solutions. Does unique continuation hold for these components? So what's unique continuation? Unique continuation is telling me that if there is some set where a function is vanishing in some open subset or my domain, then necessarily it must vanish everywhere. Solutions of many elliptic problems cannot vanish in open sets. They really need to be either zero everywhere or always different from zero except from a set of measure zero. So let us now consider a more general system, possibly critical or subcritical. The potential now, we are just asking for some integrability. The beta ij's now can be whatever, can be competitive or not, or cooperative or mixed. It doesn't matter. The question is, for this problem, the omega is a connected open set, not necessarily bounded or anything. If I find a solution, does the weak unique continuation property hold? So, for example, we can try to elucidate this particular property. If I find my vector of solutions, that is a solution of my system, and it vanishes in some open subset, do I get that the solution vanishes in the whole of omega? This is what we're going to call the weak unique continuation property for the system. All right? Well, let's see again. What happens for one equation? For one equation, we have this nonlinear problem, and it's well-known fact that the weak unique continuation property holds. For instance, by Jensen and Koenig, who showed the following. If you have a potential W in L n halves, and you have a function that satisfies this inequality in omega, then necessarily the weak unique continuation principle holds in omega. It cannot vanish in any open subset of omega. So, okay, for one component, we have unique continuation. What about two components? Or L components, but let me take the power P bigger or equal to. So only in dimension 1, 2, and 3 I can do this. Then I can also use what I know about one equation in order to say things about every component of my system, because I can rewrite my system as this. I just put all the terms of the competition part in my, let's say, potential, treat this as a potential, and if my solutions are well behaved, and typically by regularity theory they will be smooth and bounded, then I can apply the result by Jefferson and Koenig and get my weak unique continuation principle. Okay, so perhaps it holds all the time. Let's see. The problem is that if I start considering P between 1 and 2, which is always the case if I start with dimensions 4 or larger, I cannot do the same trick. So I need something else. And there is this worrying counterexample to weak unique continuation principles that we should have in mind. So if I take a sublinear power and I consider the following ODE in R, then this problem has the following explicit solution, which basically looks like this. So here T0 can be any real number. So let's take T0 equal to 1, my R, and let's say that here is my T0 equal to 1. So this explicit solution looks like this. I am 0 before 1, and then starting on 1, I grow. Well, this is an explicit solution of this ODE, and it doesn't satisfy any kind of unique continuation. So sublinear powers are dangerous for unique continuation, and this is exactly the kind of nonlinearities that we have in our system with exactly the same sign. So here the sign is important, but this is what we will have for competitive systems. So if my beta is negative, some of my coupling terms where the sublinear coupling appears has this negative sign. So there is some chance that unique continuation doesn't hold for cooperative systems in the sublinear regime. So there is this key observation that will at least give us some partial result. Although there are terms in these coupling terms that are sublinear, if I look at the system as a whole, I remember that the system has a structure, then I can still find some superlinear behavior here. What do I mean is this inequality. I take here my right-hand side. Then I can bound this right-hand side in terms of the Euclidean norm of the vector of solutions. And if I do this, I always get a superlinear power. So this is very good. Now I can try to use this trick and this structure to prove a unique continuation. And this is what we did in collaboration with Victor Hernandez Santamaria and Monica Clark. We generalized a little bit the result from Jefferson and Koenig for systems. So if we have a potential which is in L and halves, and we have a family of solutions of components UI that each of them satisfying this inequality. Here we have the Euclidean norm of the vector of solutions. Then unique continuation holds. If the whole vector vanishes in some open set, then it must vanish everywhere. Now we are asking that all of the components vanish in the same open set. In this sense, then they must vanish everywhere. The proof is done via a Kahneman inequality, which is the same one that Jefferson and Koenig used. And with this, we can show the unique continuation principle for our system. So if we have a solution of our competitive system and all of the components vanish in an open subset, they must vanish everywhere. Unique continuations are a wonderful tool. Okay, so before I go to the application, let me tell you that we can improve the result a little bit to what it's called the strong unique continuation property. It's not necessary that they vanish in an open set. It's sufficient that they vanish in one point, but quick enough. This is what we call vanishing of infinite order at a point. And a function vanishes of infinite order at a point if this limit holds. The idea is just that it goes to 0 very quickly. So if there is this one point where things go to 0 very quickly, then unique continuation also holds. The system will satisfy the strong unique continuation property if all of the components go to 0 very fast at one point, then they must go to 0 everywhere. Now to the application. Sorry, before the application. There is this one very interesting open question that we tried very hard to answer and we couldn't. We have shown that if all of the components vanish, then they almost vanish everywhere. But what happens if they vanish in their own set and the other components are different from 0? So let's say this situation. Here I'm considering two components. Let's say that this is my ui, my u1, my u2. So now one component is different from 0 in some part and 0 somewhere else. But the other component is different from 0, where the first one was 0, and then 0 somewhere else. Can this happen? Is this a possible instance for a solution of this kind of sublinear systems? We don't know. Some days we think it's possible, some days we think it's not. So it's a very interesting open question that we couldn't answer. Now, once you have unique continuation, you have non-uniqueness results together with Pohochaev type identities. This is like a usual strategy to find non-existence, and we have this non-existence result. If we consider a critical system in a star-shaped domain that has a non-empty complement, then these kind of problems cannot have a non-trivial solution. So thanks to our unique continuation and with some Pohochaev type identities for systems, we can prove this non-existent result. We cannot expect to find solution in star-shaped domains that have a non-trivial complement. All right. So what about the decay of solutions? Can we say something when we're solving a system in an unbounded domain? Can we say how it goes to 0? They must always go to 0 because we're only looking at energy solutions. So they always go to 0. But how do they do? Do they go exponentially fast? Do they have a polynomial decay? So this is the last result that I'm going to talk about today. And let's see what we found. We are considering now a system which is subcritical, potential equals to identically 1. And we are, with our usual coupling terms, we don't care if it's competitive or cooperative or mixed or anything. We want to say something about the decay of all the types of solutions that this system can have. So what is the decay of solutions at infinity? We're looking at this in Rn. All right, so we are assuming that we have a solution, and let's see if we can characterize the decay. Again, let us begin with one equation. So if I look at the Schrödinger equation, elliptic Schrödinger equation, which would be this one, then it's well known that these solutions will decay exponentially fast. Here, this potential appears also in the decay rate in the exponential, and this is a consequence of results by Ackermann, Dancer, Javier, and Stuart. All right. Maybe we can expect exponential decay all the time for our system. But then again, there is this sublinear problem because there are counterexamples of problems that have sublinear nonlinearities that do not satisfy the exponential decay at infinity. Let me show you how you can construct your own counterexample. Take W, a function C2 in R. So here we have R. Define your W as x to the power minus 2 over 3 outside the ball of radius 1. So here you have 0, 1, minus 1. Here you have a power decay. And since our function is C2, inside it can do whatever. It doesn't matter. You just put whatever you need in order for it to make it C2. Now, you build the equation in a very cheap way because you look at minus W B prime plus W, and this is going to be equal to a coefficient times W to the 1/2, where C is what it has to be. It's the equation over W 1/2. So clearly, this will cancel out with this, and this is my left-hand side. So the equation holds trivially. What's interesting is now the structure of the problem that we have just found, because we have an equation that is solved in the whole of Rn with a sublinear power on the right-hand side and a potential that goes to 0 as x goes to infinity. this is the same structure that we have in our system if you look at it. So I will have my derivatives, my potential, and then some coefficient that goes to 0 at infinity, because all my components go to 0 at infinity. And we have here a sublinear power. So, okay, now we have reasons to doubt. Is it going to be exponential, or is it going to be a polynomial, or maybe something in between? Let's see. So we show that using, again, the same trick that we use for this unique continuation, that we can use the structure of the system and find some supercritical control. Then we show that the exponential decay always holds. So whenever we have our system, it doesn't matter if we have sublinear, superlinear powers, we always have exponential decay at infinity. This is done by comparison principles and using this superlinear structure of the system. And finally, this is the last result that I want to show you today. We can generalize a little bit more our result. We can consider different potentials for each equation, and if my potentials are Holder continuous and they do not go to 0 at infinity, so at infinity they go to some constant, then I can characterize the exponential decay of each component where the rate of decay is connected to this limit of the potentials at infinity in this way. So this is everything I wanted to tell you today, a little bit of an overview of the results that we have obtained in the past 3 years. These are the papers where you can find more information. We had a lot of fun understanding these problems, so I hope that you also had some fun hearing about them. So thank you very much.
Thank you very much, Alberto. Thank you very much for your nice talk also.
Thank you.
Before asking for questions, does somebody has a question or a comment?
Maybe I can ask a question about, do you hear me?
Yes.
Yes.
Yes, okay. It is about the decay at infinity, okay? Because if you take just one of the equations, one equation, okay? Yes, for instance, this one, okay? Then you can use the maximum principle by finding a super solution, which is in fact exponential of minus square root of 1 plus x squared. Okay. So if you plug this into, one has to prove that U is bounded. Once you know that U is bounded, okay, then you can show that the solution has is less than some constant exponential of minus square root of 1 plus x squared. I take this function because this function is C infinity. While if you take exponential minus norm of x, it's not C infinity. Okay, so then I wonder whether for the case of 2 equations, since the right-hand side globally is of order of p, not each term, but globally is of order p, whether one can, once you can show that the vector u1 ul is bounded, okay, is an infinity, then I wonder whether you cannot show the exponential decay by constructing an upper super solution, if you wish.
My intuition is that you probably can, because exactly the elements that you mentioned are the elements used in our proof. We also use the maximum principle. We use comparison functions.
Okay.
We got to this bound because this is the arguments that were used by Ackermann, Danzel, and Javier Stuart, which were our main sources. to get into these type of problems.
Okay.
But from what you mentioned, these are the same elements. So my intuition is that it should also be possible to do this
Yes.
for a system of L equations.
Yes. Okay. So I agree. Okay. So that's it.
Thank you.
Another question?
The segregation and percolation in connection with the phase transition, if you have some application for that?
No, we didn't consider any problem connected with percolation so far.
Okay. Okay. Okay, thank you. Thank you very much.
Thank you.
Another comment or question? I have two. Okay, so one of them is a suggestion, maybe. So I think there are some results by Jonea Price and Luis Escauriaza where they prove Kahneman inequalities, but or why unique continuation property, not for open sets, only for positive measure sets. So maybe you can see these papers, maybe they have use for you. I don't know. I was thinking about these results for the unique continuation property.
Thank you
And
for the
also
suggestion.
I have a question about the competitive systems. You put a result or non-existent result of time-wheel solutions, but I think that in this case you are considering when you have segregation. No? What happens if you don't have segregation?
Okay. Thank you for the question. So if you don't have segregation, then you don't expect this kind of behavior for this type of systems. In fact, let's say that you have cooperative behavior. So when beta is positive, then they want to be together because they're stronger together. They are helping each other. So typically, these kind of solutions overlap. Sometimes you can have that your set of solutions is very simple. It's just really the same component, just repeated in every equation. So cooperative systems would like to be together, and therefore you don't expect to have pinwheel structures there. Only when there is some segregation. And if you have something mixed, these instances is more complicated, but maybe you can study this by like batches. If there is some batch of functions which are cooperative, and they team together with some other batch of functions which are cooperate between them but are antagonistic to the other, then maybe you can start studying some structure in this way. We didn't, but I know that there are some results working with the system for beta positive and beta ij's mixed, and you can find some structure there. You can find some particular types of solutions that find some symmetries, and it's not completely out of reach, but for this pinwheel structure, I don't think you can find it unless you are fully competitive. This is my intuition.
Okay, thank you very much. Are there any questions or comments?
Ya, después pregunto, por favor, después.
I have one question. It's about the unit continuation that you have shown. Since you have a system, so we have more than two components. Is it possible to do anything if you try to prove unit continuation if you have n-1 component, L-1 component that vanish in some open set, then all the components vanish everywhere.
Okay.
Do you know if it is?
Thank you for the question. I do have an answer. So the thing about this system is that it allows what we call semi-trivial solutions. So if you look at the system and you, let's say, I don't know, L equal to 2, for instance, and one of them is 0, and the other one is different from 0, the equation is completely fine. I mean, what will happen? It will happen, perhaps it will be easier if I go to my examples at the beginning. Here, you see, if you look at the solution, but one is 0, well, you only lose the coupling terms, no? So of course, one is satisfied trivially, and the other one, you just arrive to an equation. So the fact that some of the components vanishes does not impact on the other components because they are completely fine with it. So this is a system that allows semi-trivial solutions. This is why we call it weakly coupled. Whenever you have that, when one vanishes, the other must vanish, we will say it's strongly coupled. For instance, Hamiltonian systems. No? There are unique continuations for Hamiltonian systems. Now, if one vanishes, then the other must vanish, and this kind of things can happen. But these weakly coupled, if some of them vanish, then the other one can happily leave. Yeah.
Okay. Okay, thank you.
Thank you.
One question about the connection with the Bose-Einstein condensate. How is this explication? I don't understand that.
So my understanding of physics is very, very low, but this is what I understand. This is what I know. You look at the Schrödinger system, and then you want to find some standing waves. To find the standing waves, you need to solve a system like this. And then what's the information on each of the components? Well, this is like a quantum situation. You take the component, you square it, and then this one is giving you some density function on two quantum states on a very cold material. These are more or less like the elements involved in the physics behind the Bose-Einstein condensates, but it's definitely not something that I would claim I understand deeply. I just know there is a connection, and that some physicists are interested in this particular case because of this, because with the solutions of this system, you can build standing waves, and the solutions will give you information on some density functions.
Disculpe que hablo en español, pero usted dice que ahí usted está hablando un comportamiento ondulatorio. ¿Está dando ahí una explicación ondulatoria o...? Porque ahí usted me dice ondas estables, la parte
Sí.
estática, en el régimen estacionario, ¿a eso se refiere usted?
Hay ciertas como ondas viajeras, según yo entiendo, y entonces hay manera de encontrarlas poniendo un ansatz, ¿no? Un ansatz de una función que está multiplicada por cierta exponencial, y entonces vas a buscar ciertas funciones que te van a permitir que tu ansatz resuelva la ecuación de Schrödinger con tiempo y con su parte compleja. Entonces, resolver este sistema es uno de los pasos que necesitas para construir una solución del sistema de Schrödinger.
Claro, bueno, lo entiendo, claro. Claro, en ese caso, si usted me habla de Schrödinger, entonces habría que analizar las autofunciones, las energías también fundamentales, la energía fundamental. ¿A eso se refiere usted también cuando calcula energías asociadas a ese sistema? Porque si hablamos de Schrödinger, ecuación tenemos que hablar en autofunciones y también las energías principales de este sistema, ¿no?
Es mi entendimiento que el hecho de que se llame funcional de energía es porque detrás está justamente la energía de este tipo de sistemas físicos.
Entonces, claro, ahí se daría lo que usted dice, el estado fundamental, ahí estaría probando energía mínima, los estados, claro, porque la ecuación de Schrödinger justamente es para eso, ¿no? Para establecer las energías que se dan en el sistema, ¿no? Porque si yo no tengo las energías, entonces, ¿cómo yo voy a poder calcular una estimación estadística, ¿no? De las amplitudes, ¿no? De las amplitudes. Si usted me dice que alguna amplitud va a decaer, entonces necesariamente yo tengo que mirar la energía, ¿no? La energía principal que me va a servir, como usted dice, de guía, si esa amplitud cae o no cae, ¿no? Por decir, en otras palabras, las funciones de onda aquí, si lo vemos con Schrödinger, me van a localizar las soluciones. Si usted me dice que son soluciones positivas, es muy interesante también. Pero sí, le agradezco su explicación. Está bien.
Gracias por la pregunta.
Muchas gracias también a usted.
Diego.
Okay, so thank you, Lucero. Thank you, Alberto, for